Hello friends, today I am going to discuss about radar system. So, following are the topics which I am going to discuss now. Basic principles, pulse systems and other radar systems. So, let's have a look on history of radar. History of radar starts with experiments by Heinrich Hertz in the late 19th century that showed that radio waves were reflected by metallic objects. This possibly was suggested in James Clerk Maxwell's seminal work on electromagnetism. Now, what is radar? Radar is basically a means of gathering information about distant objects or targets by sending electromagnetic waves at them and analyzing the echoes. And radar stands for radio detection and ranging. So friends, now let's have a look on this video how radar will help to control a system. Light and reliable, a cable and pulley flight control system transmits the rotation of yoke to the pilot. Here it's showing how the person is getting the signal from radar and control the system. When the pilot rotates the yoke, a sprocket jet rotates, setting off the condition of movements down the length of the steel or stainless steel. Now discuss about the basic principles. In essence, a radar consists of a transmitter and a receiver, each connected to a directional antenna. The transmitter is capable of sending out a large UHF or microwave power through the antenna. The receives much energy as possible from the echoes reflected in its direction by the target and then treat and displays this information in a suitable way. So, what is the fundamental of radars? Here I have shown you basic block diagram of a radar. First, transmitter, receiver, duplex and the antenna. In response to an internally generated trigger signal, the transmitter generates a short rectangular pulse. As soon as a small fraction of the pulse power is fed to the duplexer, this device disconnects the receiver from the antenna and connects the transmitter to it. Now, development of radar. Nowadays we are having compact radar rather than large antennas. It will consume less space as compared to olden radars. So now we should know on what frequency radar works. The frequencies employed by radar lie in ultra high frequency and microwave ranges. The next topic is radar performance factors. On what factors radar works, and that factors is described on the basis of radar range equation. Later I will discuss that equation. Here some band names are given, UHF, L, S, like this, and their frequencies are given, and on the basis of radar range equation we are finding maximum available peak power, or we can say maximum peak power available in a tube. As suppose for UHF band, it's having 5 megawatt maximum available power. Now I'll discuss radar range equation. Why we have to use radar range equation? To determine the maximum range of a radar set, it is necessary to determine the power of the received echoes and to compare it with the minimum power that the receiver can handle and display satisfactorily. So, power density is given as P divided by 4 pi r square, where P is the peak value of the power and r is distance from antenna. Now we'll see pulse radar system. Here we'll have discussion about pulse system and followed by a discussion of scanning and display methods. Pulse radar can be divided into search radars on one hand and tracking radars on the other. Finally, some can mention about auxiliary systems such as beacons and transponders. Here I have shown you block diagram of pulse system, trigger source, modulator, output tube and others. In that block diagram, main points are modulators, antennas and scanning, and antenna tracking. So first we'll discuss about modulators. In a radar transmitter, the modulator is a circuit or group of circuits whose function it is to switch the output tube on and off as required. There are two main types in common use: line pulsing modulators and active switch modulators. The latter are also known as driver power amplifier modulators and were called hard tube modulators until the advent of semiconductor devices capable of handling some modulators. So the next topic is antennas and scanning. Radar antennas are often made to scan a given area of the surrounding space, but the actual scanning pattern depends on the application. Here I have shown you some typical scanning patterns. The first one is horizontal, in which we will be able to see 2D view, and the next one is noding scanning, in which we will get the output in waveform, and the third one is helical scanning, and the fourth one is spiral, in which the distance between the main lobe and the axis of rotation will be more as compared to the horizontal scanning. Now we will discuss antenna tracking. Auxiliary methods of tracking or precise location must be employed. The simplest of this is the lobe switching technique, which is also called sequential lobing. And the next one is B part. Conical scanning is a logical extension of lobe switching, which is shown in figure. It is achieved by mounting the parabolic antenna slightly off center and then rotating it about the axis of parabola. Now we have studied about radar and the history of radar and different types of factors which will depend on the control system. Now display methods. The output of a radar receiver may be displayed in any of a number of ways, the following three being the most common displays. The first one is a scope display method, and the second one is plane position indicator, and the third one is direct feeding to a computer. So first one is a scope. The operation of this display system is rather similar to that of an ordinary oscilloscope. A sweep waveform is applied to the horizontal deflection plates of the CRT and moves the beam slowly from left to right across the face of the tube and then back to the starting point. In the next point, I'll discuss plane position indicator. Here, some position are showing in position indicator. The PPI display shows a map of the target area. Here, we should mention like main runways, parked aircraft, control tower, aircraft landing, and radar site. And the next one is direct feeding to a computer, in which we'll get the signal directly through the radar on our computer. After all this discussion, we have observed there are multiple clutters. So one of the methods of eliminating clutter is the use of MTI, which employs the Doppler effect in its operation. So on the basis of MTI, we have observed emitted wave are moved to the target and again reflected to the transmitter. The distance between the target and the transmitter, which is showing in the form of waveform. Now radar beacons. A radar beacon is a small radar set consisting of a receiver, a separate transmitter and an antenna, which is often omnidirectional. The presence of a beacon on a target increases enormously the distance over which a target may be tracked. Such active tracking gives much greater range than the passive tracking so far described. Now I am going to discuss about other radar systems. The first one is CW Doppler radar, frequency modulated radar, phased array radars and planar array radars. First, CW Doppler radar. A CW Doppler radar sends out continuous sine waves rather than pulses. There are many advantages of CW Doppler radar. It is capable of giving accurate measurements of relative velocities using low transmitting powers, simple circuitry, low power consumption and equipment whose size is much smaller than that of comparable pulsed equipment. The next one is frequency modulated CW radar. The greatest limitation of Doppler radar, that is its inability to measure range, may be overcome if the transmitted carrier is frequency modulated. So we use frequency modulated CW radar to eliminate the limitation of Doppler effect. Now we can overcome all the limitations using phased array radars. It will give very significant improvement in versatility if a moving beam could be produced by a stationary antenna. The next and the last is planar array radars. The planar array radars uses a high gain planar array antenna. A fixed delay is established between horizontal arrays in the elevation plane. As the frequency is changed, the phase front across the aperture tends to tilt, with the result that the beam is moved in elevation. In first diagram, I have shown you frequency scanning as used by planar array radar causes radar beams to be elevated slightly above one another. And in the second figure, planar array radar showing 5 separate groups of fine beams which permit scanning of 27.5 degree of elevation. I tried to share few information about radar system. Hope it's informative. Here I have assembled few queries for your reference. Please go through, and if you like my video, don't forget to click like. Thank you for your patience and time. I am Priyanka Yadav from CMRIT, closing my topic.